Warm good morning to all. Now we are going to see about introductions of thermodynamics. Therm means heat, dynamics means power. So the study of energy and its transformation was studied in thermodynamics. There are four laws are present in thermodynamics. First one is zeroth law, which deals about temperature. First law, it deals about internal energy and enthalpy, and second law of thermodynamics deals about entropy change, that is entropy of a system. Yes, and in third law of thermodynamics, it was not considered as a law, but it describes about the entropy of a pure solids. So thermodynamics involves the study of flow of heat or any other form of energy into or out of the system as it undergoes a physical or chemical transformation. In studying and evaluating the flow of energy into or out of the system, it will be useful to consider changes in certain properties of the system. So these properties include temperature, pressure, volume and concentration of the system involved. And measuring the changes in these properties from the initial state to final state can provide information concerning the changes in energy and related quantities such as heat and work. There are three empirical laws in thermodynamics. The study of thermodynamics is based on three broad generalizations derived from well-established experimental results. So the generalizations are known as first, second and third law of thermodynamics. These laws have stood the test of time and are independent of any theory of atomic and molecular structure. The scope of thermodynamics is most of the important laws of physical chemistry, including one-half law of lowering of vapor pressure, phase rule, distribution law, can be derived from law of thermodynamics. It tells whether a particular physical or chemical change can occur under a given set of conditions of temperature, pressure, and concentration. It also helps in predicting how far a physical or chemical change can proceed until the equilibrium conditions are established. Though it is having applications, thermodynamics is also having some limitations. Thermodynamics is applicable to macroscopic systems consisting of matter in bulk and not to a microscopic systems of individual atoms or molecules. It ignores the internal structure of a system and molecules. Thermodynamics does not bother about the time factor of a reaction, and it does not tell anything regarding the rate of physical change or chemical reaction. It concerns only with the initial and final stages of a particular system which is involving in physical and chemical changes. So before we study about the laws, we should know about the system and surrounding. So a system is part of the universe which is under thermodynamic study, and the rest of the universe is called as surrounding. So here we are having a representation of a system and surrounding, and the real or imaginary surface which is separating the system from its surrounding is called as boundary. So we are having many systems in that the particular part is homogeneous and heterogeneous system. When a system is uniform throughout, it is called as homogeneous system. If we dissolve water, if we dissolve salt in water, after solubility the solution is uniform. So if we are having the uniform distribution of a substance, then it is said to be homogeneous. So examples are a pure single solid, liquid or gas, and a mixture of gases, and true solution of a solid in a liquid. For this only I have given the solubility of salt in water. So a homogeneous system is made up of only one phase, and a phase is defined as homogeneous, physically distinct or mechanically separable portion of a system. A heterogeneous system is one which consists of two or more phases. In other words, it is not uniform throughout. For example, ice in contact with water. Water is in liquid phase and ice is in solid phase. Ice in contact with vapor. So here ice is in solid phase and vapor is in gaseous phase. So here ice, water and vapor constitute separate phases. So there are thermodynamic systems. So we are having three types of thermodynamic systems depending upon the nature of the boundary which is separating the system and surrounding. If the boundary is closed or sealed, no matter can pass through it. So if the boundary is insulated, no energy can pass through it. So isolated system is when the boundary is both sealed and insulated. So no interaction is possible with the system and the surrounding. Therefore, an isolated system is one that can transfer neither energy nor matter from its surrounding is called as open system. Here and let us consider a system of 100 ml water in contact with vapor in closed vessel which is insulated. Since the vessel is sealed, no water vapor can escape from the bottle. Also, because the vessel is insulated, no heat is transferred with its surrounding. So a substance, say boiling water contained in a thermoflask, is another example of isolated system. Closed system, here the boundary is sealed but not insulated. Therefore, a closed system is one which cannot transfer matter but can transfer energy in the form of heat, work and radiation to and from its system, that is from its surrounding. A specific quantity of hot water contained in a sealed tube is an example of a closed system. While no water vapor can escape from the surrounding, it can transfer heat through the walls of the tube to surroundings. So a gas contained in a cylinder fitted with a piston constitutes a closed system. As the piston is raised, the gas expands and transfers heat in the form of work to the surrounding. And finally, we are having open system. In such a system, the boundary is open and uninsulated. Therefore, an open system is one which can transfer both energy and matter to and from its surrounding. Hot water contained in a beaker placed on laboratory table is an open system. The water vapor, that is matter, and also heat, that is energy, is transferred to the surrounding through the imaginary boundary. So zinc granules reacting with dilute hydrochloric acid to produce hydrogen gas in a beaker is another example of open system. So hydrogen gas escapes and the heat of reaction is transferred to the surrounding. So and we have to know about the properties of a system. That is, there are two types of properties. First one is intensive and second one is extensive properties. So intensive properties, a property which do not depend upon the quantity of the matter present in the system, is known as intensive property. Some example of intensive properties are pressure, temperature, density and concentration. If the overall temperature of a glass of water in our system is 20 degree Celsius, similarly, if the concentration of a salt, NaCl, that is sodium chloride, in the glass of water is 0.1 mole per liter, then any drop of water from the glass also has a salt concentration of 0.1 mole per liter. So extensive property means a property that does not depend upon the quantity of a matter present in the system is called extensive property. Some examples of extensive properties are volume, number of moles, enthalpy and Gibbs free energy. Some of these properties are unfamiliar to you, but these will be defined and illustrated later. By definition, the extensive properties are additive while intensive properties are not. Let us consider the system, a glass of water. If we double the mass of water, the volume is doubled, and so is the number of moles, and the internal energy of a system is also doubled. So intensive properties: temperature, pressure, density, boiling point, surface tension, refractive index, viscosity, and freezing point. And the example for extensive properties are mass, volume, internal energy, enthalpy, and entropy. So there are some states of variables. A thermodynamic system is said to be in a certain state when all its properties are fixed. The fundamental properties which determine the state of a system are pressure, temperature, volume, mass, and composition. Since a change in magnitude of the properties alters the state of a system means these are referred as state variables or state functions of thermodynamic parameters. It also stands to reason that a change of a system from initial state to final state will accompanied by change in the state variables. It is not necessary to state all the properties to define a system completely. For a pure gas, the composition is fixed automatically as it is 10%. The remaining state variables pressure, volume, temperature are interrelated in the form of algebraic relationship that is called as equation of state. So for 1 mole of pure gas, the equation of state is PV equal to RT. For ideal gas, PV equal to nRT. Here we are considering for the equation for 1 mole of a pure gas. So it is N is equal to 1. We are writing it as PV equal to RT, where R is constant if of the three state variables pressure, volume and temperature. Pressure and temperature are specified. The value of third V volume is fixed automatically and can be calculated from the above equation of state. So the variables pressure and temperature which must be necessarily specified to define the state of a system are designated as independent state of variable, and the remaining state variable which depends on the value of pressure and temperature is called as dependent state variable because it depends pressure and temperature. An important characteristics of a state variable is that when the state of a system is altered, the change in the variable depends on the initial and final state of the system. For example, if we heat a sample of water from 0 degree Celsius to 25 degree Celsius, the change in temperature is equal to difference between the initial and final temperatures. That is, change in temperature delta T equal to temperature of final state minus temperature of initial state. That will be equal to 25 degree because we are subtracting 25 from 0, so it is 25 degree. So the way in which the temperature change is brought about has no effect on the result. So thermodynamic processes are there. When a thermodynamic system changes from one state to another state, the operation is called as process. So these process involves the change of conditions, that is temperature, pressure and volume. So there are various type of thermodynamic properties based on the above conditions, that is temperature, pressure and volume. So first one is isothermal process. Those processes in which the temperature remains fixed are termed as isothermal processes. This is often achieved by placing the system in thermostat, that is in constant temperature path. For an isothermal process, change in temperature dT is equal to 0. The next one is adiabatic process. Those processes in which no heat can flow into or out of the system are called adiabatic processes. Adiabatic conditions can be approached by carrying the process in an insulated container such as thermos bottle. High vacuum and high polished surfaces help to achieve thermal insulation. For an adiabatic processes, change in heat, that is dQ equal to 0. The next one is isobaric process. Those processes which take place at constant pressure are called isobaric processes. For example, heating of water to its boiling point and its vaporization takes place at same atmospheric pressure. So these changes are therefore designated as isobaric process and said to take place isobarically. So for an isobaric processes, change in pressure, that is dP equal to 0. The next one is isogoric processes. Those processes in which volume remains constant are known as isogoric processes. So the heating of a substance in non-expanding chamber is an example of isogoric process. For isogoric processes, dV equal to 0, that is change in volume becomes 0. In cyclic process, when a system in a given state goes through a number of different processes and finally returns to its initial state, the overall process is called as or cyclic processes. For cyclic processes, internal energy, that is change in internal energy, dE equal to 0 and dH is equal to 0. Thank you.